this down, so I have to start this up before I can start my lecture. I just realized that. Sorry about that. So we'll be a moment. If you could just take down the information on the board. I have absolutely no control until this starts. There we go. Displays, screen up, screen down. Hi, everybody. Welcome back. Thank you for handing in your homework. Thank you for the Post-it notes. Okay, so today we're going to be discussing work, circulation, and flux. So now this is the first combination that we'll get between this new concept of vector fields and the concept of the concepts we have understood from integration up till now. And I think we should motivate this concept from where it was motivated from originally, which is from Newton's laws. Okay? So we should go really and motivate it. The book, they write a definition down. I think it needs to be motivated a little better. Okay? So today we'll discuss the work done by a force vector field. Remember, a force is a vector field. I plotted some examples of vector fields last time. So we're going to understand the work done by a force, which is a vector field, in its action of moving an object from one point to another. And to understand that, we begin with Newton's law. This is the second law, acceleration equals force divided by mass. Okay? Now, there's something going on here, which is a little subtle. We write this down, and we don't realize all the time that there are subtleties to this statement. And one of the subtleties is that F is a vector field. F is a function of x, y, and z. But A is an acceleration. Therefore, it is the time derivative of velocity, which itself is the time derivative of a position. And we understand that that position vector is from a curve. So let's say we have x, y, z space here, x, y, z. And we have a curve r of t. And the acceleration is the second derivative of this position vector. Here is the position r at some given t, say t0, the second derivative of this position vector. Okay? Where t now is truly time. We really mean time parameterizations now. We're really into the physics of this all. R is a position as a function of time. So what do you mean by this? The right-hand side here is a function of, apparently, a function of x, y, and z. And the left-hand side is a function of t, right? V is a function of t, and f is a function of x, y, and z. But if you think about what you mean by this statement, let's think about what we mean by this statement. We mean the acceleration evaluated at the curve. Like as you're moving, you feel that acceleration. So you have to evaluate the force on the curve. Okay? So what we mean by this statement is, although the force is understood, we understand that there's force everywhere in space. I could draw that vector field out, put all the arrows in R3 if I wanted to. When I put it into this equation, I must evaluate the force on the trajectory, on r of t. And so from that perspective, what we have is the following statement. M, d, I'm going to write this out. Actually, let me write it out completely. Let r of t, I'm going to write its components, and I'm going to use capital x, y, and z. Because little x, y, and z I will reserve for the Cartesian coordinates. But capital X, capital Y, and capital Z are the functions of time. So R of t is x of t I hat plus y of t j hat plus z of t k hat. These are uppercase because I consider them to be functions of time, whereas x, little y, and little z are just the Cartesian coordinates. And so this statement over here says the second derivative, in particular the second derivative of x, this is capital X with respect to time, I hat, plus m times the second derivative of capital Y with respect to time, j hat, plus m times the second derivative of z with respect to time, k hat, equals the force vector field, F, not as a function of little x, little y, and little z, but evaluated on this trajectory, x of t, y of t, z of t. Often I will use x vector, little x vector, to denote a general point in R3, whereas R vector, which is a function of t, denotes the points along a curve. Like the curve I've drawn up there. Okay? So x means any of the points. X vector means any of the points. R of t means the points that are on the curve. So Newton's law is best understood as this equation. And since this has components, an I hat component, a j hat component, and a k hat component, in fact, if you take a look at this equation as written, these are three equations, one for each component, each of which is second order. Okay? And so a second order ODE, second order because it has two derivatives. We call this second order. You'll learn this a little more in differential equations class, okay? Second order. And so the combination of the whole thing is actually a sixth order system because it's possible that all the forces, like the force you feel going in the x direction depends on where you are in the y and z. So it couples all of those different functions together, okay? And that's the material of ordinary differential equations. But we don't have to get into the weeds of that just to understand some properties of Newton's law. Okay? So I'm not going to always write it like this. I'm going to stick with the shorthand that we have up above. M dv dt, that's m dv dt, which is mass times acceleration. And this is the form I want to use, because this is the form everything's going to work out nice in, is equal to the force, not as a function. See, this is f of x vector here. This is f of x vector here, but this is f of r. And that's what I want to realize. This is f of r of t, okay? And all this says is your mass times the acceleration you feel is the force you experience at where you are, okay? Now I'm going to do something which I hope is not too mysterious. I'm going to take the dot product of this equation with the velocity, okay? And this is a vector equation, which means it's those three, but when you take the dot product, you go from three equations to one equation. This is a function of time, and in some sense, we do not know what R of t is. To get R of t, you have to solve this system, and that's ODE class, that's 22b. So you take the dot product with v. So I got v, which is a function of time, right? V is a function of time because we see that R is a function of time, and v is simply its derivative. So I have v dv dt is equal to v dot f of R of t. All I've done is take the dot product of both sides. Whatever you do to one side, you do to the other side. That's what an equation has to maintain equality, you got to do the same thing to both sides. Okay. Now, we have to make an observation. Okay? And the observation we make is the following. We make an observation of the chain rule. Okay. And I'm going to write it out explicitly one more time. Well, do I need to write it out? The observation is this. V dot dv dt is equal to the time derivative of the magnitude of v squared over 2. Or put differently, this is the time derivative of v dot v, because that's the magnitude of v squared divided by 2. Okay? Squared. Okay. This is a straight up application of chain rule. This is a straight up application of chain rule. Okay? Now, how can I'm going to show it to you by hand. Okay. It's not that challenging. So remember, v is the time derivative of r, but let me let v vector, let me call its components capital U, which is a function of t, I hat, plus capital V, which is a function of t, j hat, plus capital W, which is a function of t, k hat. Again, I told you this was fluid dynamics notation. I think I used it last week. Just components of that vector, okay? Each of these are the time derivatives of x, y, and z. Now, v dot v, the dot product of v with itself, is simply u squared, which is a function of t, plus v squared, which is a function of t, plus w squared, which is a function of t. And if I take its time derivative, so this, by the way, is what I mean by the magnitude of v squared. That's what we mean, the length of v squared. That's how you calculate the length of a vector squared. If I were to take the time derivative of the length of v squared, whatever I do to one side, I must do to the other. That's the time derivative of u squared, which is a function of t, plus the time derivative of v squared, which is a function of t, plus the time derivative of w squared, which is a function of t. Now, I've skipped a step here, right? I've distributed the time derivative over each of these terms of the sum, but you know the derivative of a sum, the derivative of the sum is the sum of the derivatives. Okay? You've proven that in Calc 21a. Now, the next step is a straight-up application of chain rule, even though we don't know what u of t is. We don't need to know what u of t is. The time derivative of a function of t squared is 2u times du dt. This is straight-up multiplication. This is not dot product. That's just chain rule. Okay? And of course, it's all the same for all these. Even though we don't know what u, v, and w are, it's the same. So the next one will be 2v dv dt, where this is not v vector. This is the component v. And then 2w dw dt. And I hope you see now that this is just u. So this is just v vector dotted into the time derivative of v vector times 2. And that's the time derivative of the magnitude of v vector squared. So if I just divide by 2, I get that result up there. Okay. I go through this in detail because I want you to understand that sometimes people get confused with this. Sometimes people get confused with chain rule a little bit. But this is what chain rule means. So this is important. That means I can pull the time derivative out front here, and I'm going to pull it right out front of everybody. And I have d by dt of m times the magnitude of v squared over 2 is equal to v dot f of r of t. Okay? Now, not all of you are taking physics, but nonetheless, calculus was born with physics at the same time, at least our modern notion of physics, physics of prediction, physics of solving these equations, thinking about predicting where a trajectory goes. We pause for a moment and look at this equation, and we should always consider what are the units of this equation. And what are the units on the left-hand side? Well, mass is measured in kilograms. This is kilograms meters squared per second squared, divided by seconds. So this is kilograms meters squared per seconds cubed. Okay? Therefore, the right-hand side must have the same units. I haven't done anything mysterious to it. And you may you look over here and you're like, hey, I knew that mv squared over 2 is something I've heard about in the past. Okay? And so, in fact, this is going to be called, we're going to come up with a name for this. Right? We don't know what it is yet, right? Except we do, or many people might. But we don't. We came up with this idea, we as a society, we as scientists, came up with this idea by going through this calculation. And whomever did it, I'm pretty sure it was Newton, realized that, hey, I can actually derive what's called a conserved quantity. Okay? I can derive a conserved quantity for this equation. But I can't do it just yet. I can't do it just yet. Okay? But this is going to have units of kilograms meters squared per second squared. And this is kilograms meters squared per second squared divided by time. So this is the time rate of change of this quantity. And this quantity measures your velocity squared. Something about your velocity squared times your mass. And that combination changes if, look what's happening, if your velocity is not perpendicular to the force. If it's perpendicular to the force, if your velocity is perpendicular to the force, this dot product is 0. Okay? So since I don't really want to insult your intelligence and act like nobody's ever seen that expression before, many of you have seen that expression before, I'm going to tell you that the right-hand side has a name, is called the power expended by the force. And if you look at it, since it is a dot product, it is a dot product of the force at where you're located, wherever that m is located, dotted with the velocity of that particle. So if they are perpendicular, there is no power expended. Okay? Now we just do a very simple thing. When you have a time derivative in front of, I've pulled this time derivative out. See? This time derivative was sort of it's between two terms, okay? But now that I've pulled it out in front of everybody, I am ready to exploit the fundamental theorem of calculus by integrating this equation, okay? And so now we integrate this equation. Okay, so the first question is, integrate with respect to what? Okay? Well, I told you this is all a function of t. So the only thing you can integrate with respect to right now is t. Okay? So let me integrate with respect to t. And if I do that from the left-hand side, I'm going to do it from some start time, which I'm going to call t0, to some end time, which I'm going to call t1. These I'm using because it's going to be a definite integral. And that is d by dt of m modulus of v. And I'm going to emphasize that this is a function of t squared over 2. I integrate that with respect to t. And whatever I do to the left-hand side, I best do to the right-hand side. V vector, I'm going to emphasize that it's a function of t dotted into f, which is a function of r of t. And I'm integrating that with respect to t. By the fundamental theorem of calculus, the integral of a derivative is just the function evaluated at the upper bound minus the function evaluated at the lower bound. So this left-hand side simply becomes m times v vector of t evaluated at the upper bound, which is some t1 squared divided by 2, minus m times v vector of t0 squared divided by 2 is equal to the integral t0 to t1 of v of t dotted into f of r of t dt. And now I'm going to give you the remaining names of everything here. You might know if you pay for your electrical bill, right? You pay for the total amount of electricity, which is in kilowatt hours, well, which is energy divided by time times time. That's total energy, okay? A watt is power, energy per unit second, per unit time, joules per second, okay? This is the change in kinetic energy. Kinetic energy is the energy, the change in kinetic energy. Okay, first, there's just two questions. I've just told you this, boom, decreed this, like I know something more than you do, right? I don't, in the sense that, okay, I've memorized these things, but what do we mean by these ideas, right? The word kinetic comes from the Greek for motion, okay? Energy So there's this mysterious thing that we know about, sort of, right? Where does energy come from? Well, it's going to come from what we're going to see in the next section, which is a conservation law, which will arise from this equation in a moment. But it doesn't arise just yet. Okay? So energy is the idea that there is another thing in Newton's law that is conserved, sometimes, maybe often. But we haven't figured it out yet. We haven't figured out what that whole energy is. But we can see that, we will see that these are pieces of that energy, and they deal with the motion of the particle because they deal with the velocity of the particle. Okay? This, therefore, has a name. This is the work done by the force. The work done by the force on the particle, on the mass. Okay? And so this statement is the following. The difference in the amount of kinetic energy you have at the end of some observation time compared to what you had at the beginning of that observation time is equal to the integrated amount of power expended during the time of flight, during your trajectory. This is called the work. So when people ask, why do we have to do line integrals, this is one of the most important reasons why we do line integrals, right here. This one right over here. Okay? So let me look at that line integral in a couple of ways. You'll notice that hidden in that line integral is v vector, right? So you see v vector. So we're going to let's say that the work here, I'm going to look on the right-hand side. The work is defined as the integral from t0 to t1. I'm going to rewrite the dot product. Let's just switch the order because it'll make life a little more convenient. V vector of t dt. Okay? I'm going to rewrite this equation as follows. I recall to you that v vector is equal to the unit tangent times the magnitude of dr dt. Right? We got that from last time. That's why we studied chapter 13. That's why we spent some time in chapter 13. And this is the magnitude of the velocity, which is also the speed, which is also the time rate of change of the arc length of the curve, ds dt. And so the work gets rewritten, the integral from t0 to t1 of f of r of t dotted into the tangent vector, which depends on where you are. I'm going to emphasize the tangent vector does depend on t. Right? You're either pointing this way or this way, your unit tangent, times ds dt dt. And I hope you see now that this is right for expressing as the integral with respect to arc length. And so we rewrite that. There's different forms. These are all just equivalent forms. Okay? Different ways to look at this result. Okay? So let me just say, this is the most natural beginning point because it really comes from the dynamics. Okay? But effectively, I'm pointing out that this has length over time times time. So the times are going to cancel out. That's where I'm going here. Okay? And that's what I'm about to see, that these times are going to cancel out. And what you're going to get is the integral of f of r dot t hat ds along the curve. That's another way to look at that. And what this says is, oh, it actually it just doesn't depend on the time parametrization. Because this dt and this dt effectively cancel out. There's effectively a chain rule here. And this is how did we do line integrals? When we were confronted with a line integral, which was some function along the curve integrated with respect to arc length. This is an s, everybody. This is my sloppy s, arc length. Function along the curve integrated with respect to s. We parametrized that curve and went this way, and basically went in this direction, or up to this point at least. But now I'm sort of undoing it because what this emphasizes is that it doesn't really matter. The t doesn't really matter in this problem. Although we need a time to get a parametrization, it's really weighted by ds, these arc length, these pieces of arc length. Okay? So that's another way to look at it. A final way to look at it, the book uses, it's called the differential form. I don't like to use the differential form of these equations, and the reason I don't like to use the differential form of these equations is I think this is the most definite way to do things. Okay? You have an f of x, you have an r of t, you substitute x as r of t, you take the dr dt, and you do this dot product, and you do the integral. Bam. Okay? Instead of like doing dx's and dy's and dz's in the differential form. I just don't find it to be the most convenient. That being said, what the differential form recognizes is that each component of v dt can be written as, I'll write it out, the integral f dotted into dx I hat plus dy j hat plus dz k hat. This is v vector dt, because v is dx dt, dy dt, dz dt. Okay? And then and this is the integral along the curve of this quantity, where this is the function evaluated along the curve. Okay? And then the book completes it by saying let f equal m I hat plus n j hat plus p k hat, where these are the three components of f. And so the math textbook writes the work done as the integral along the curve c of m dx, where this is a function of x, y, z, plus n dy, where this is a function of x, y, z, plus p dz, where this is a function of x, y, z. Okay? I'm writing it down because it's in the book. I never, to this day, use a form like this. Okay? This is what I call a formal way of looking at it. And if you have one preferred way over here, you're like, I'll always get it right if I write. I'm back. Sorry. Okay, so if you have one way that you can get it right all the time, then do it your way, okay? So that's work. That's where work comes from. That's where the notion of work comes from. And the reason we care about work is because it's related to this change over here. It's related to this change. Doesn't want me to speak. Did I hit it again? Did somebody see me hit it again? No. Oh, battery. Let me take a second, and there's a problem with the battery. Well, I'll just look at it. Because you all want to hear my voice tomorrow and hear this lecture again. It's so good, right? Okay, here we go. No, there's a problem with the battery. Give me 2 seconds, everybody. Talk amongst yourselves. Okay. So, example. I'm going to stick with the example that really, like an example that really works, okay? So, So when you do these examples, you will be given a trajectory, r of t, and you'll be given a vector field. Okay? What I'm going to do for you is I'm actually going to solve the trajectory, which is the trajectory that you had on your quiz yesterday, which was the trajectory of a particle being launched on a parabola. Okay? We're just going to do constant gravitational field. Okay? So this is going to be z. This is going to be x. I'm going to have m dv dt is equal to negative mg k hat. Okay? And I'm only going to do this one in 2 dimensions because I've already noted that you could just rotate into the direction that you're launching at. I'm going to start with initial conditions with x0 equals z0 equals 0. And I'm going to start with an initial velocity u0 equals u of 0 equals v0 times the cosine of an angle, cosine of alpha, and v of 0 equals v0 times the sine of alpha. And so alpha is your pitch angle here where you throw that baseball at that angle. Okay? So if we go through this problem, I did this for the drag problem, but if we go through this problem, we should realize that x of t is equal to t times v0 times the cosine of alpha. And z of t, and y of t is going to be 0, so I'm just going to make that equal to 0. And z of t is equal to t times v0 times the sine of alpha minus gt squared over 2, where g is a gravitational constant. Okay? So I would like to point out that notice, so at t equals 0, what is my mv squared over 2? mv of 0 squared over 2 is equal to, well, just the magnitude of the initial velocity vector, which is m times v0 squared over 2, where v0 is this constant over here. So this is the vector evaluated times 0, and this is what it is. It's v0. Okay. Now, let's consider the work done. Okay? What is the work done by this force? What is the work done by the force? Okay? So that's equal to, work is equal to, well, we know we're going to start at time t equals 0. So start at time t equals 0, and let's choose a time t1 for my end time. Okay? The end time is just going to be called t1. And we always write down the definition. I've told you what the definition of work is now. It's f of r of t dotted into v of t integrated with respect to t. So what this says is the following. Take the vector field, evaluate it along the trajectory, and then dot it into the velocity. Okay? I haven't explicitly written out r of t, but let me just do it. R of t is always the x component I hat plus the y component j hat plus the z component times k hat. So r of t is equal to t times v0 cosine alpha I hat plus, I'll put this in parentheses, t v0 sine alpha minus gt squared over 2 k hat. That's r of t. That'll give the parabola. Okay? V of t is just the time derivative of that, which is v0 cosine alpha I hat minus gt k hat. Oh, no. Sorry, plus v0 sine alpha minus gt, all in parentheses, k hat. Okay? So now the work is equal to the integral from 0 to t. Well, the force field, the force vector field is just negative mg. This happens to be a very simple vector field. Okay? It's negative mg, sorry, k hat. It's a very simple vector field. So there's nothing really to evaluate there, which makes this problem a little bit too easy maybe for an example. But it's a ubiquitous problem. So it's negative mg k hat dotted into v of t. Well, v of t is this object here. And if you don't mind, I'm not going to write it. Okay, because it's right above. And then integrated dt. Okay? Well, the force is all in the k hat direction. The force is all in the k hat direction. Therefore, when you take the dot product with the velocity, this component drops out because k hat dot I hat is 0. And k hat dot k hat is 1. So the only thing that survives this dot product is the k hat component of the velocity in this case. Okay? And so the k hat component is going to be, I'm going to have the work done by this force is equal to negative mg, which I'm pulling out front, times the integral from 0 to t1, wherever I decide to stop observing this work being done, times v0 sine of alpha minus gt. And I have to integrate this function with respect to t. And that's a simple integral. You notice, ideally, that most of the integrals we get in this class are somewhat straightforward. It's the setting up, it's the conceptualization that's really important. And so this is going to be negative mg v0 times sine alpha, I'll open parentheses here. Well, this is a constant, so this is just t1 minus 0, which is t1. And this is going to be minus g t1 squared over 2. So this tells you actually what the change in kinetic energy is. It tells you the kinetic energy later on minus the original kinetic energy is going to be this function of the later on of time t1. Okay? But what's something interesting about this equation? If you take a look at the term in parentheses right now, you'll see that, hey, that's just z of t. In this case, it happens just to be z of t. Notice? Take a look at z of t and z of t. Okay? So in fact, this is z of t1. Right? The height at t1. Which tells you something, okay? So let's just say delta KE is the change in kinetic energy. Delta we like to use for the change in kinetic energy. So I'll just call that change in kinetic energy. For this simple classical problem, that's equal to negative mg z of t. And notice what happens. Well, the change is always, so we're imagining a ball being thrown above the ground. So z, we're always going to have z is 0 or positive, right? If it hits the ground, z goes to 0 and the whole process ends. When it comes back to the ground, the change in kinetic energy is 0. That means it comes back to the ground with the same kinetic energy that it left, which if you've ever caught a ball hit by a batter, you realize that, especially anybody who plays cricket, you really realize that, right? Because you don't have gloves, okay? And it hurts, okay? So this is 0 when z is 0, and z is 0 at 2 points in the trajectory, at the beginning and when it hits the ground. And it's maximal, right, when z is at the top of its flight. Woo, okay? At the top of its flight. That's when it has the greatest decrease in kinetic energy. But that doesn't tell me that the kinetic energy goes to 0. It does not go to 0, in fact. It doesn't go to 0. But it tells me that it is decreased the most at the top of its flight. in this specific example right here. Okay? Now, you'll be offered more in a math class, in a math textbook. You tend to be offered questions of this form because a little bit is just a straight up practice line integral. So let me try a different one, okay? I don't know, let's try this one right here. So this is a question that now gets sort of, I'm going to divorce this from the physics. The physics is the association of the right-hand side with the left-hand side. That's the physics of the problem, okay? I wanted to show you the physics. I wanted to motivate this problem, or else it has no motivation. Here's an integral. The mathematics is, let's just work with integrals of this form. Let's just work with integrals of that form, okay? So now this is another example. Let f equal, I'm going to let it equal one of the vector fields, one of my basic vector fields that I had back on Monday, okay? I think it was a vortex vector field. I'll just make f be a vortex vector field. Okay? So f is going to be negative omega times y, omega times negative y I hat plus x j hat. Okay? And if you recall, this vector field for omega positive looked like it was swirling around the axis this way. I showed you how it got bigger as the distance got farther away. So it's this kind of swirly vector field. Okay? And now let's just make some trajectory. Let's make a trajectory, okay? This is the kind of problem you'll get. Let C be curve starts at origin at 0, 0, goes on a straight line, S-T-R-A-I-G-H-T line, to, I don't know, let me go A, comma A. Okay, we're to A, comma A. So A, comma A is going to be like a point up here, right? It's going to go on a straight line from here to here, okay? And then goes up to, let's make it go up to A, comma 2A. A, comma 2A, also on a straight line. Okay, these are the kinds of questions you might be confronted with. And we need to think about what this is going to do, okay? So you begin the problem by writing down what work is. Work is equal to the integral. Well, any of those forms count. Any of those forms are equivalent to one another. So I'm just going to write the integral along the curve C of f of r, evaluated on the curve, dotted into the tangent vector to the curve, integrated with respect to s. Okay? No, I want to do this curve. I want to do this thing parametrically. I'm going to tell you this. I can teach you 1,000 things, right? But if I teach you one thing that I can show you 1,000 ways to do it, or I can show you the one way that will always work and it's kind of straightforward, maybe I should just show you the straightforward way and not the 10 other ways. Even the book sort of suggests doing the other ways. I'm just going to do the one way. Parametrize the curve. Just always parametrize the curve. Okay? Make your life easy. Parametrize your curve. The issue here, the reason I did C in this abstract way, just C, right, is the curve C is this piece and this piece. Why are the two pieces? Because there's a bend there. It's not continuous. Right? So really, when I parametrize the curve, I have to parametrize this one first and then this one second. Is that OK? So what I would write is C is given by C1 plus C2, the sum of those two curves. The first curve and the second curve. Okay? Well, C1, that's easy peasy. Sorry, C1 colon. That's given by R of t equals, well, A times t times I hat plus j hat. That's what the curve is. That's it. That's a straight line going on a tangent vector, which is 1 I hat plus 1 j hat. This is not the unit tangent, but it's a tangent vector. Okay? It goes from, at t equals 0, it's at the origin, and at t equals 1, it's at the point AA. It's a straight line. So for 0 less than or equal to t, which is less than or equal to 1. Okay? So that's the first curve. The second curve, well, I can reuse a parameter. I can reuse t and start it again. Or I can parameterize from t goes from 1 to 2 or something like that. Okay? So shall we let t go from 1 to 2? Because t goes from 0 to 1 on here, I can make t goes from 1 to 2 over there. Is that okay? So the second curve is r of t. Now at t equals 1, it better be at a comma a. Right? And the x component of it doesn't change at all. Right? So this is going to be at a times I hat. The I hat component is not going to change. It's always going to be x equals a. The j hat component, at t equals 1, it better be at a. And at t equals 2, it better be at 2a. Oh, that's pretty easy. That's it. But you have to emphasize, you have to emphasize that 1 less than or equal to t less than or equal to 2. Is that good? This is really easy. I just parameterized these two curves. Okay? Now, I talked it through. Okay? You might need more talking through for your own purposes, especially straight lines. Always think about the tangent vector, just the direction it's going in. And you just got to figure out where your beginning point is and where your end point is. You know, if you're not comfortable with this, you always can hold on to the fact that r of t for a straight line is r0 plus t times v0, which this is a tangent direction and this is some shift, right? You just have to figure out the components x, y, z here and u, v, w here. But I did draw the line out once. Okay, well, let's do the work. The work is equal to the integral. Now I'll just make it the integral along the curve, which is the integral from 0 to 2. We'll use the time integration. F of r of t, this vector field evaluated along the curve, times, well, dv dt dt. Okay? I wrote the arc length version of it over there, but I'm going back to the parameterized version. So I think that is the one that will always work for you. Now, since the curve is defined in two pieces, I really need to split this integral up into those two pieces. And so I'm going to write that as the integral from 0 to 1 of f of r of t times dv dt, sorry, times v. Yeah, okay, I didn't make a mistake before. I just made a mistake. See my mistake? It's not dv dt, it's v. Right? It's v. I'm sorry about that. See that v over there? That's the v. That was always v. Right? I'm dot plotting with v. This is dr dt is what I meant here. V is dr dt. Okay? I could lie to you and say that was a sloppily written r, but my voice lied. My voice already told you the truth, so dotted into dr dt. Okay, and then I integrate that with respect to t, plus the integral from 1 to 2 of f of r of t dot dr dt dt. Now, this is the only thing that is at all conceptually novel about this, okay? But the next step. You have to evaluate f along the curve, okay? So remember, I have f of xy is equal to omega times negative y I hat plus xj hat. Okay? That's f. That was the one that I gave you at the beginning. But in the integral, I have to evaluate x is x of t, and y is y of t. X is the x of t on the curve from here to here. Y is the y of t on the curve from here to here. So on C1, on this curve, f of r of t is equal to this same omega. Now y, what is y along C1? Well, I wrote it. Along C1, y is at. Okay? That's what you got to do. That's the only to it. Okay? That means I'm evaluating it on the curve. So y is at. So this is negative at because of that negative there. I hat. What is x? Is at also in this case. Okay? Okay? What is dr dt? Dr dt along this curve, this is also on C1, okay? On C1, dr dt is equal to a I hat plus a j hat. So I just took the time derivative of r of t on C1. These are the pieces that are going to that first integral. Y'all okay with this? So this is the thing that you just got to be careful of. You're like, okay, where do I put the x? You go to the curve, you evaluate, figure out what x of t and y of t is on the curve, you substitute it in. You're not always going to get a simple function like this. It might be a nasty function, but you still just substitute it in. So I'm going to stay on this board because I want to keep working so you see it all in one eye shot kind of thing. Take the dot product. So in the first integral, f dot dr dt, and I realize I'm at my limit here. Take the dot product. What's the dot product of these two vector fields? 0. You didn't need to go through all of this to see that it was 0. The vector field is swirling around the circle. That first line is going radially. So everywhere you go, it's perpendicular. Everywhere along that diagonal line, it's perpendicular to the vector field. So it's 0. So that whole integral is 0, and I don't have to bother with it. Okay? On the second curve, you do the same thing. And I beg your indulgence for 10 more seconds, please. On the second curve, you have to evaluate the vector field on the second curve. But on the second curve, I just erased it. On the second curve, y is equal to at. And so I have a negative at I hat because it's negative omega y, right? It's negative omega y. And y is equal to at. And x is equal to a. So that's omega x.